Hi guys, welcome to A-Level Chemistry and Physics. And today we will be covering a rather small part of a large topic in the S-level syllabus. Today we will be covering electric current, potential difference, and resistance. And this further bridges into other concepts like Kirchhoff's law, resistance and resistivity, and so on. But today we will be covering these topics. Okay, so let's get into it. So we have to talk about what's inside a metal wire. Okay, and we do this because metal wires are the most common conductors we use in electrical circuits. Right, so a metal has a different structure than most other materials. Okay, so in metal, instead of having atoms which are fixed in position with a nucleus and electrons orbiting around them, has free electrons. That means in the lattice structure, the nucleus of the atoms is in place. These ions you see, right? This is where they form the lattice structure. The electrons, which are usually just orbiting around the nucleus, are instead completely free to move throughout the structure. So these electrons are in constant motion. They can move left, right, forward, backward, etc. So just the positive ions are in place, and the negative electrons keep flowing all throughout the structure, right? Yeah. Then, so what happens inside the wire when a battery is connected across it, right? So when a wire is connected to a battery, the wire now has a positive and negative terminal attached to it because battery has a positive and negative terminal. So and we know that electrons, because they're negatively charged, will flow towards the positive terminal, right? So as we know, there are freely flowing electrons in the wire. So these electrons flow towards the positive end of the battery. This movement of electrons is what generates a current, right? Current is basically the movement of charged particles from one point to another point. So in the metal wire, it is the electrons that move from towards the positive terminal generating a current. Do note that the positive ions do not move from their positions at all in a metal wire. They stay grounded right into their place. So charge carriers. So by definition, just for explanation purposes, this is not the exact definition. The charge carriers are essentially any charged species capable of movement. Electrons, plus two ions, plus three ions, negative two ions, anything. Right? In the case of the wire, for example, the electrons are the charge carriers, right? Because they are free to move and their movement generated a current. But there can be different charge carriers, and we will examine one other example in the next slide. Okay. We talk about an electrolyte. Okay, and there is a diagram which is in the next slide, so it will help you understand. So, what is an electrolyte? An electrolyte is usually a salt which is dissolved in a solvent, right? The salt is usually an ionic solid, an ionic compound, and it is dissolved in a solvent. Sorry. When dissolved, the salt separates into its ions, right? So if there is NaCl, when this is dissolved in water, the Na and Cl separate and they become freely flowing Na plus and Cl minus ions. So positive ions, in the case of NaCl, there is Na plus. In the case of negative ions, it is Cl minus, right? So when you're conducting electrolysis, that means connecting a metal battery to two metal plates and inserting into the electrolyte, we know that the positive ions move towards the negative plate and vice versa, right? Because obviously opposite charges attract. So both these type of ions move in opposite directions. The positive move towards the negative end, the negative ions move towards the positive end, and because there are charged objects moving in opposite directions, this also generates a current. So it is not always that just has to be the negative ions generating a current. In this case, because they're oppositely charged ions moving in opposite directions, both of these lead to generation of a current. And so we can conclude that in an electrolyte, it is the ions that are charge carriers and generating current. In the metal wire, they're electrons, but in an electrolyte, they are ions. So this is the diagram I was talking about. So we have a battery, positive plate, negative plate. The negative ions move towards the positive ions move towards the negative plate, and their continuous movement to opposite ends generates a current. This is what these are the charge carriers in an electrolyte. So current and charge. Okay, this is a new subtopic we're starting, and we obviously mostly just known of them as two different quantities. However, they're related while we study current and electricity. So Whenever a charged particle flows through a specific point in a circuit, we say that there is a current in the circuit, right? So in a circuit, when there are electrons and there are electrons constantly, a stream of electrons constantly moving past a point, they generate a current. Electrical current is measured in amperes, symbol A. So how much charge is moving when there is a current of 1 ampere? Right? So we just established that charge and current are somewhat related, but once you come down to the numeric calculations, how much charge passes a point when there is a current of 1 ampere. Right? So charge is measured in coulombs. So charge and current are related by the following equation. Current is charge over time. I have not included this here, but charge, the symbol for charge is Q, the symbol for time is T. So current is charge over time. Therefore, just from this equation, we can derive a definition that current is defined as the rate of flow of charge. When you say rate of something, it is the value divided by time, right? So flow of charge, so charge is over here divided by time. And then we can further use this equation to uh, define charge or define one unit, the coulomb, which is the unit for charge. We can use this equation to define the coulomb, right? So current was charge over time. We took time to the other side, so charge becomes current into time. This gives us a definition of the unit of charge, the coulomb. One coulomb is the charge which flows past a point in a circuit in a time of 1 second when the current is 1 ampere. 1 into 1 will give you 1. So in symbols, the charge flowing past a point is given by delta Q is equal to I delta T. Here the triangle sign is delta, which means change. So delta T is essentially T final minus T initial. That is the time in between. So delta means change. So this is an important equation. It comes very often, and you should memorize this. Now we come to another value known as the elementary charge or E. So charge we know is measured in coulombs. However, at the subatomic level, when you come to electrons, protons, the using coulombs as a unit becomes very tedious and very complicated because the charge on one electron is minus 1.6 in 10 to the power minus 19. As you can see, because the 10 to the power minus 19 is there, using it in equations, constantly cancelling the value of 10 to the power minus 19, etc., becomes very complicated. So we introduced a new unit known as elementary charge where the value of E is equal to 1.6 into 10 to the power minus 19 coulombs, which made it easier to deal with calculations at a subatomic level. So the charge of electron is minus E, the charge of a proton is plus E, right? So protons are positively charged, the charge of plus E, equal and opposite to that of an electron, which is minus E. Also, ions carry charges that are whole number multiples of plus E and minus E, right? So because electric charge is carried by particles, and the smallest particles, protons and electrons, carry charges in multiples of E. There are also quarks, which are subatomic particles. We covered particle physics in another video, which have fractional charges, but again that does not count because we always find them in groups where the total charge of a proton, which is made up of three quarks, will always be a whole number multiple of E. So for example, 3.2 to 10 to the power minus 19 C this charge can exist because it is 2e, right? An integer multiple. But 2.5 into 10 to the power minus 19 C is impossible because it is not an integer multiple of e. So whenever you're doing calculations, etc., and a question asks you whether this type of elementary charge can exist and the number is a non-integer multiple of e, 1.5 e, 2.5 e, then you have to say that it is impossible for this charge to exist. Okay, so we also come to a new equation for current. Okay, this is I is equal to NAVQ. Okay, this is very important as well, and we will dissect this equation variable by variable in the next slides. So N stands for the number density of the material. Okay, and by definition, a number density is defined as the number of conduction electrons per unit volume. So essentially, although this is obviously not possible, if you wanted to calculate the number density, you find the total number of electrons in a block of metal divided by its volume. That is essentially the number density, right? And we also know that metals have an internal structure of freely flowing electrons which cause current. They are not held in orbits by any of the nucleus. They freely flow throughout the whole structure, right? But when you compare, for example, copper to sodium, copper will have a higher number of free electrons per unit than sodium. Now, why is that? Because sodium forms Na plus ions. That means for every atom of sodium, there is one free electron present in its structure. But once you compare that to copper, copper forms Cu2 plus ions. That means each copper atom releases two electrons, whereas sodium only releases one. So per atom, there are twice as many electrons in copper than in sodium. Therefore, we can safely say that copper will have a higher number density than sodium. This is just a result of the way in which different metals form ions. If there is another metal which forms 3 plus ions, that will have a higher number density than copper because per atom it would release 3 electrons. And then there are some other obvious variables that don't need in-depth explanation. A stands for the cross-sectional area of the wire. V is called the mean drift velocity of the electrons, which is essentially the average speed of the electrons moving in the wire. This will most probably in the papers be given to you if there are any equations involved. So you don't need to know this very often. As the name suggests, it is just the average speed of the electrons moving in the wire. Q stands for the charge of the particle carrying current, right? Because Q is always charged. But in this situation, we are calculating it for a wire, and the particles which are carrying the current are electrons, and electrons has a charge of minus C. Therefore, we can replace Q with E in this equation. Okay, so I picked this out because this was a very good explanation and derivation for the equation. Okay, so now imagine that you are timing the electrons to determine that speed. Okay, you plug in a battery, turn it on, and then you start a timer from when the electron starts from the left hand side and emerge from the right hand side of the wire. And you stop the time when the last electron, which is a part of the wire, comes out of the second end. Okay, so your time will show that this electron has taken time t to travel distance L. T is the time taken by the electrons and distance L is the length of the wire. Okay, so once you have to so in time t all the electrons have come out of the wire. Okay, now once you have to calculate how many electrons are present in the wire, what we can essentially do is multiply the number density, which is number of electrons per unit volume, into the volume of the wire. That will give us the total number of electrons present in the wire, right? So that is number density into volume. Volume is area of cross section into length. So this is volume, this is number density, and multiplying these three will give us the number of total electrons present in the wire, right? And then the charge of the electrons. Charge of the electron, one electron has a charge of E. This time we are discounting the uh, negative charge because negative current does not exist, right? We have to just take the modulus or eliminate the negative sign. So the total charge is the number of electrons multiplied by the charge of one electron. So total number of electrons as derived here is NaL, and we multiply that with E, right? So now we have the total charge present in the wire. Now we can find the current because as we've seen in the previous equation for current is rate of flow of charge or charge over time. So this is the total charge and we have to divide it by T. This gives NaLe upon T. Length over time, right? Because this whole thing is in a bracket essentially. So L over T or length over time is essentially velocity, right? Because distance over time is velocity. So we substitute V, which is the mean drift velocity of the electrons, for L over T, which is distance over time, which gives us the equation NaVe. Sometimes, occasionally, the derivation of this equation will also come. So I advise you to do it and redo it and understand the logic as many times as possible. Because this is actually, if you understand this, the entire concept of number density, mean drift velocity of electrons, as well as this equation will become crystal clear, which is important for later knowledge, and so on. Right now we come to potential difference and EMF, or electromotive force. So we know roughly what potential difference is or voltage is, but this time voltage is actually made up of two terms, potential difference and electromotive force, right? So potential difference by definition is the potential difference between 2 points. So once you calculate the potential difference between 2 points A and B, the potential difference refers to the energy per unit charge moving the charge from point A to point B. So if you have a circuit setup, you have a bulb and you put a voltmeter across it. The voltmeter across the lamp essentially displays the energy per unit charge for the for the charge to move across that lamp. That is what potential difference is. It is always calculated across any other component or so on. Electromotive force, on the other hand, is defined as the total work done per unit charge when a charge flows around a complete circuit. So this is not electromotive force is never done across a part of a circuit. Electromotive force is the total work done by one unit charge and moving across the whole circuit through all bulbs, all buzzers, all other appliances, and then when it comes back to the battery, the total work done for it to move throughout the whole circuit is what is EMF. This is very important. Then we come to electrical resistance, right? So resistance for any component is defined as the ratio of potential difference to the current. This is this is derived from the equation for Ohm's law, which I pretty sure you already know. V is equal to IR, so R is equal to V divided by I. So therefore we can define the ohm, which is the unit of resistance, from this expression. Ohm is the resistance of a component when a potential difference of 1 volt drives a current of 1 ampere through it. That is, the object has a resistance of 1 ohm. Electrical power, again, this is also very interesting and very important. So again, power, as I explained in a previous video also, power is the energy transferred per unit time, right? The rate of transfer of power is what a rate of transfer of work is what is power. Power is measured in watts, symbol W. So, and as the explanation or the definition suggests, power is work done upon time taken. But when we do electrical components and study electricity, the rate at which energy is transferred in an electrical component is related to two quantities. If it has a higher current across the component, and if it has a higher potential difference. If both of them are very high, the power and work done will be large, and if it is less, the power will be small. So what we can do is the fact that we know that the power is directly proportional to current and voltage, we can derive an equation from these two proportionalities. Okay, so the amount of energy W transferred by a charge delta Q when it moves through a potential difference V. Okay, and I'll come to the equation in the next slide. Right. So as you know, work done is the charge or delta Q traveling across a potential difference of V, right? Because that is how we define voltage. If you rearrange this, V will give you W upon delta Q. And potential difference is the work done per unit charge in the transfer of a charge from point A to point B. So this is just rearranging the original equation into W is equal to V delta Q. The original equation is V is equal to W over delta Q, which comes from the original definition of potential difference, work done per unit charge. Okay. So now let's come to the derivation. Power is work done per unit time, right? We established that before. Here work done is V delta Q upon delta T, right? So we substitute this here and we get, so what we do is we segregate delta Q by delta T because this gives another quantity. The ratio of charge to time is essentially just the current of the component, right? Because the rate of flow of charge by definition is current. So we substitute this with the symbol for current I. So P, or the power, becomes voltage, which has come from here, and current. Current substitutes this. So as a word equation, we have power is equal to potential difference into current, And now we have also have the connection between watts, the unit of power, which is equal to amps, the unit of current, into volts, which is the unit of potential difference. So yeah, guys, that's all. And I thank you so much for tuning in. I hope you found this useful. Do hit the subscribe button because we need to get this knowledge to as many people as we can. Leave a comment below if you have any suggestions or if you want me to take up a specific topic. For now, I will keep continuing with the AS level topics, and then I will start with the A level physics topics. Thank you for watching. Bye bye.